Andrei Kolmogorov was one of the giants of 20th century mathematics. He, among other things, helped shape probability theory into the rigorous field that we know today. Then, in the late 1950s, near the end of his career, he turned his attention to a deceptively simple but deep problem: how to represent multivariable functions. Around the same time, his student, Vladimir Arnold, was beginning to make a name for himself, and he later became famous for contributions in dynamical systems and geometry. Together, the two of them uncovered something remarkable. First, Kolmogorov proved that any continuous function of several variables can be represented as a finite sum of continuous functions of just one variable, combined through addition and composition. 2 years later, Arnold sharpened and clarified this result, showing in more detail how such decompositions could actually be constructed. Their work became known as the Kolmogorov-Arnold representation theorem. For decades, the theorem lived mostly in the realm of pure mathematics. That changed in recent years, when researchers in machine learning realized that this old theorem could serve as the blueprint for a new kind of neural network. Neural networks, at their core, are universal function approximators. Mash this idea up with Kolmogorov-Arnold representation theorem, and the design practically suggests itself. Instead of relying on fixed activation functions at each node, why not build networks where the connections themselves carry learnable univariate functions? That's the idea behind Kolmogorov-Arnold networks, or KANs. Each connection is parameterized with splines and a base function, which allows the network to adapt its building blocks during training rather than forcing every neuron to behave in the same rigid way. The beauty of this approach is twofold. First, KANs are usually more interpretable than traditional multilayer perceptrons, MLPs, because the functions they learn along each connection can often be inspected and understood directly. This means you get insights into the structure of the underlying data. Second, they can often achieve competitive performance with smaller networks than their MLP counterparts, since their architecture is better aligned with the mathematics of function decomposition. This makes them attractive in scenarios where you want not just a black box predictor, but also a model that offers some explanatory power about how inputs combine to produce outputs. That all being said, KANs are not a silver bullet. Just like other neural networks, their performance depends heavily on the quality of the training data. And here lies a practical challenge. Generating or collecting good quality training data, especially high-fidelity scientific data, can be costly and time-consuming. For this reason, KANs are particularly well-suited to applications in scientific machine learning, where interpretability is valuable, model sizes must remain modest, and where you can carefully curate or augment datasets. But they can struggle in cases where data is sparse, noisy, or highly irregular. And that's where today's paper comes in. In it, the authors developed something called MFKANs, Multifidelity Kolmogorov-Arnold networks. They are built specifically to combine large amounts of cheap, lower-quality data with small amounts of expensive, high-quality data, so that you can train KANs more effectively. On today's episode of Journal Club, we'll explore how MFKANs work and walk through more of the mathematical foundations that make this possible. If you're already subscribed to our email newsletter, then you'll be getting this full episode in text, audio, and video form delivered to your inbox in the next few hours. Journal Club, the latest academic research explained in plain English.